So this is the start of a new unit called Discrete Functions. So this first part is sort of describing a little bit about what discrete functions are. They are a bit different than the other functions we sort of studied in the rest of the course. But in general, for most part, we're going to talk about discrete functions mainly as sequences and series later on in the unit. But today, or this lesson is sort of an introduction to discrete functions or sequences in general. So here's a quick warm-up, and what I really like about this unit is one is very practical, and at least the start of here, to me, it's almost like problem-solving puzzles. So we're sort of giving a puzzle that's numbers-based, and then we sort of have to solve the puzzle a little bit. So a warm-up is a little bit like that, where we're sort of given a pattern of numbers, and our goal is to figure out what maybe the next three numbers are. So in order to do that, we sort of have to determine what the pattern might be. So in the first question, or A, we got -3, 1, 5, and 9. The pattern that we could probably see from that is that as the numbers are going up by 4, so therefore the next three numbers would be 13, 17, and 21. The next one, it's a little bit more tricky. 27 minus 9, 3 minus 1. So it's a bit different than the first one. There's not going up or down by the same set of same value, or later on we're going to say the same difference. But we could sort of try to guess that we go from 27 to -9. Seems like a division by 3, or -3 in this case. And then we'll go from -9 to 3. And again, we're dividing by -3 here, so that seems like the general pattern that we're trying to do. And to confirm that, going from 3 to -1, we are dividing again by -3. Or in general, we can think of it as we'll multiply by a third. So our next terms after this would be -1 times a third would be, -1 times a negative third would be a third. Then we get -1/9, and then -1 over 27 as we keep dividing by, or say keep multiplying by -3rd. The next one, a little bit tricky because it's not so much how the numbers are sort of related to one another in the sequence. We got 1, 4, 9, 16. So we can't sort of use the same tricks that we did in the first two examples. But we kind of look closer. There's hopefully the numbers 1, 4, 9, 16 are a recognizable pattern in that there are perfect squares. So essentially 1 was 1 squared, 4 would be 2 squared, 9 would be 3 squared, 16 would be 4 squared. So in order to continue that pattern, 5 squared would be 25, 6 squared is 36, and 7 squared is 49. Okay, so that's a warm-up for sort of introduction to a sequence. So our success criteria for this lesson is we'll discover various techniques to determine the terms and the formula of a sequence. So I bolded 3 words there: terms, formula, and sequence. So we needed to sort of go off and define what those are, because they're going to be important for the rest of the unit. So in terms of a sequence, what a sequence is an ordered set of numbers, and there we don't want to be confused with something else, and I'll explain that in a second, but it's an ordered list of numbers, most likely identified by a pattern or rule that may or may not stop. So when we say ordered, it doesn't have to be, let's say, in numerical order or sorted. What it means is that there's a definitive list, or list, definitive order to the numbers. So if we just go back to the first example, well, it looks like it's going up in order. Actually, the second example might be even better because those numbers are not in sorted order, but they're in a particular order, meaning that 27 is the first number, -9 is the second number, 3 is the third number, -1 is the fourth number, so on. So there's an explicit order in that we know what the first number is, second number is, third number is. So this is very different than, let's say, a notion of a set, because if we have a set of numbers, there is no order to it. We just it's a group of numbers. So that's what we talk about. Sequence is an ordered list of numbers. And we'll talk about the rule later on. These next two definitions are very important, and in the past there's usually some confusion between these two. Hopefully we sort of iron out exactly what the definition of these two words are, because they're really important. So first is what we call the term. So this is a single value in the sequence. So let's go back to, I'm just going to rewrite the example that we had, maybe the first one, -3. So -3, 1, 5, 9, and ... expresses that pattern continues, so that sequence continues. So when we say a term is a value in the sequence, that means the actual numbers in the list itself. So for example, -3 is a term, 1 is a term, 5 is a term, 9 is the term. So what is the actual numbers in our sequence? The term number is sort of where is it in that sequence. So what we call the order location of the sequence. So for example, the term number of -3 is 1. The term number of 1 is 2 because it's the second number in the sequence. Likewise, the term number of 5 is 3 because it's the third number in the sequence. And the term number of 9 is 4. So we could think of this as a function. I'm going to talk about this before I talk about explicit formula, because it makes use of a specific notation. But here, what I just want to stop and talk about is really using this and this. An example is that this is a function. We could look at this as a function. So the function itself is called, it would be labeled t of n. So that's the function itself. And what does the function mean? What does the function t of n mean? So what in this case is that specifically here, t of 1 would be -3. So this function is really n is our term number. So that's the value of our variable. That's basically the term number. And then given our function t of n, which is really a sequence, we could determine what the value of t of n is given the term number. So in this case, t of 1 would be 1. T of 2 could be 1. T of 3 is 5. And t of 4 is 9. We could also look at this as an ordered pair because that's what a function is, given a value for my independent variable, in this case n, what is my answer? So in this case, we could turn this into a ordered pair. So this would be 1, because that's the first number in the list, is -3. 2, it would be 1. Then we get 5, it's not 5, sorry, 3, 5, because the term number there is 3. And the fourth is 9. So that's how we could express a sequence as a function. So one of the things that we're going to recognize when we look at a sequence as a function is that our domain of an independent variable is very limited. In fact, it's very specific. It's always going to be 1, 2, 3, 4, so on, because those are sort of like the ordered parts of the sequence. In other words, the location number. It could only be an integer value. In fact, in this case, it can only be a natural number. It can be 1, 2, 3. So usually when it comes down to this, that's when we talk about sequences as a function, is that it's very specific in that sense, in that the domain of the independent variable will always be the same. It's going to be our actual y values are going to be different based on what the actual sequence is. So when we're ever given a sequence now, we sort of shortcut it. And that's what we're going to talk about now in terms of explicit formula. So an expression that represents any term t of n. So recognize that T of n, it's written in a special way. When it's written like this, we know that we're talking about a sequence. It's really, as you can look at it, as a function notation. So again, mathematicians are efficient. They don't like writing the brackets when it comes to dealing with sequences. They should have shortcut it and say, well, we're going to use T of n in this case, and n is subscripted. So here we could say, given a sequence, we could express that T of n, and we could make a general equation for it, saying that what is the sequence relative to its term number. So in this example, we could say that T of n, so let's look at this example, what is the pattern that we're already detecting over here? So if we were sort of graph it, let me sort of graph it maybe over here. Let me just graph it over here. Okay, it may look something like, well, there's 1, -3 might be somewhere down here. 2 and 1 may be somewhere over here. 3 and 5 might be somewhere over here, and hopefully we can kind of see that this is eventually going to be forming a straight line if we connect the dots, but we're not, because that's not the function itself, but it is linear. So in this case, we may say that T of n, well, what's the slope of this? The slope of this is 4, so 4n, and what would be the y-intercept? Well, here going back down 4 would be something like that, -7. So here we can say that's a general or explicit formula, or we're talking about general formula of this sequence. And here if I plug in 1, it does work. So 4 times 1 minus 3, that's going to be -3, so that's what we got over there. Plug in n for 2, well, 4 times 2 is 8, minus 7 is 1, and that's going to work for the other numbers in our sequence as well. So here, this is what we call an explicit formula, or also later on we'll refer to it as a general term. So an example, we'll use the explicit formula T of n is equal to 2n plus 1 to write the first 3 terms of the sequence. So we'll do something like this. So again, let's differentiate between the term number and the term. So T of n itself is the term, what term that we want. In this case, we want the first term. We're going to start the first term. So that means n of 1. So you could think of it, if we're doing function notation, is this is what's T of 1. In other words, what's the first term? Well, we're going to write it like this because that's the notation that we use for sequences. So T of 1 in this case is going to be 2. So meaning the same thing as we're going to replace n with 1. So that's really 2 times 1 plus 1. Well, that's 3. Well, T of 2, again, we're doing the same thing. We're going to replace n with 2 this time because we want the second number in the sequence. So that's 2 times 2 plus 1, which is going to be 4 plus 1, which is 5. And then the third term, so n is in this case 3. So 2 times 3 plus 1 is going to be 6 plus 1, which is 7. So we could write the first 3 terms as 3, 5, and 7. And that's the rest of the sequence. We can sort of go on. So here's another example where we're given a sequence and we want to come up with an explicit formula. So here I'm going to write it out as an ordered pair. Maybe that would help. So here we got 1 minus 1. The second number in the sequence is 1. The third number sequence is 3. And the fourth number sequence is 5. And I could kind of see that's going up by 2. So it's sort of linear again. So let me sort of maybe draw a rough graph after this. 1 and -1 would be somewhere down here. 2 and 1 maybe somewhere over here. 3 and 3 would be somewhere over there maybe. And then 4 and 5 might be up there. So it does look like it extends as a line. So what would be the equation of a line? Well, we get the y equals mx plus b. But in this case, we're going to say T of n. So what's the slope? The slope is going up by 2 every single time. So here's going to be 2n. And what might be the y-intercept? Well, here, if there was a 0th number in the sequence, which there isn't, but let's pretend there is, because that's how we get the y-intercept, is we got to go back down 2. So that makes this one 0, -3. So that's the y-intercept is -3. So that's one way we come up with an explicit formula. In this case, where the numbers are going up by a constant amount. This next one is a bit tricky. Well, I could be honest, it's a lot tricky. So this one it's not linear. We could tell it's not linear. So if I was to sort of graph this, I'm not going to get a straight line. What would be a set of points? So it would be 1, 3, 2, 9, because that's the second number in the sequence. The third number is 19. The fourth number is 33. And the fifth number is 51. So I could graph this, and to be honest, graphing it is not going to help us that much. Only thing it will tell us is that it's not linear. But just even look at the numbers, it's not going up by a constant amount. We could tell it's not linear. So one of the things that we're going to do is sort of explore is maybe look at the first differences. So here, how do we do the first differences again? Is this minus that, so that's going to be 6. Then we're going down. 19 minus 9 is 10. 33 minus 19 is 14. And then 51 minus 33 is 18. And then let's look at the second differences. Hopefully we'll hope that they converge. So 10 minus 6 is 4. 14 minus 10 is 4. And 18 minus 4 is 4. So they do converge eventually to be a second difference of 4. So digging back into our grade 10, we realize that this is a quadratic then. So here we can say that this might be a quadratic equation. And how do we come up with the equation? Well, one of the things that if you dig deep back into your memory pockets is that what that second difference is, or a value is actually the second difference. The a value is the second difference divided by 2. So in this case, my a value is 4 over 2, which is 2. So how do we come up with the equation? Well, we know that in general, so let's go T of n is, let's write down the quadratic equation in standard form. So a n squared plus b n plus c. Now we know that a is 2. So how do we go and figure out b and c? Well, we're given some points on our equation. So let's look at the easiest 2 to look at, maybe 1 and 2. So t of 1, in this case, is 2 times 1 squared plus b times 1 plus c. And we know the value of t of 1, in this case, is 3. So 3 is going to be 2 times 1 squared, which is 2. B times 1 is just b. And then we're left with c. So we know that here, we subtract 2 from both sides, so we get 1 is equal to b plus c. So there's one equation that we could derive from this. And in order to solve an equation with 2 variables, we need 2 equations. So in this case, we'll use the second point here, or the second term in our sequence. So here, let's write it out that t of n again was going to be 2n squared plus bn plus c. So in this case, t of 2 is going to be 2 times 2 squared plus 2b plus c. And we know that the value of the second term, is 9. So we get 9 is equal to 2 times 2 squared. Well, 2 squared is 4, times 2 is 8, plus 2b plus c. So in this case, we're going to get to subtract 8 from both sides. We're going to get 1 is equal to 2b plus c. So we're going to go off and solve this equation now. So kind of looking at this is going to be kind of, so there's my first equation, and this might be my second equation. I'm going to use elimination to solve for this. And here I'm going to subtract 1 from 2. So here I'm going to get 0. 1 minus 1 is 0. 2b minus b is just b. And then luckily c minus c is just 0. What we got from here, b is 0. So let's just use this equation. So this implies that, well, 1 is equal to 2 times 0 plus c. So that makes c is equal to 1. So therefore my general term is going to be, so my general my explicit formula is going to be 2n squared plus 1. Double check. Let's see if this actually works. Well, let's use the point 4, comma 33. In other words, the fourth term in my sequence is 33. 4 squared is 16 times 2 is 32 plus 1 is 33. So it sounds like this one might work. So this one's a little bit more tricky because it was a lot harder to sort of maybe recognize what the pattern is and then coming up with that explicit formula. So let's go explore some more definitions. To be honest, this one isn't that important for this unit, but it's really, we need to be conscientious of sort of the difference between a continuous function and a discrete function. So a continuous function is a function whose graph is a curve that's no holes or jumps. In other words, it's all connected at once. So we've studied various functions in this course, and they're all continuous. So, obviously a linear equation is continuous. If we look at a quadratic, that's definitely continuous as well. Okay. Other functions that we sort of looked at in this course was the absolute, and the absolute is definitely continuous as well. Then in the last unit, we did some sinusoidal curves or functions, and they were definitely continuous as well because it was just a wave that continued on and on. The one function that we studied was the reciprocal, so 1 over x, which looks something like this. So this one is not continuous because it's not connected. So this is what we maybe call a discrete function or a non-continuous function. So it's a function whose graph is made up of separate points that are not connected. But the more blatant example is the one that we just sort of looked at, and I sort of graphed a couple of times already. So this is definitely a discrete, and this is definitely discrete. The graph is made up of points that are not connected. So that's the definition of a discrete function. So let's look at some examples of things that we could consider continuous data or discrete data. So the number of students, well, we can only have like whole numbers of students, like a 0, 1, 2, 3. So in this case, that's going to be definitely discrete. Time in a race. So how long does it take for somebody to run a race? So this one's a little bit tricky because you might think, well, this one is discrete because if I time somebody, they ran the race in 10.654 seconds. So in that sense, you might think it's discrete because it could be 10.264 or 10.265. The issue there is that time itself is not discrete. It's a limitation of our measurement. We can only measure it within a certain precision. But in reality, time is a continuous notion. In other words, if we have an instrument that can measure to the minutest point, time is continuous. Arm span, so here we're dealing with length. So again, it's sort of limited in some ways to our measuring device, but in itself, when we're talking about lengths or something, in this case the arm span, it could be anywhere within a real number. So maybe that's the idea. It could be sort of any value that could be possible. And so here we look at arm span would be continuous. There's within a certain range, of course. Your arm span can't be 100 meters, but within a certain range, any value could happen in there in terms of arm span. Likewise, when we're dealing with weight, we're sort of limited by the instrument that we can measure is, but the idea of weight again is a continuous number. It could be any value, any real value within a certain range. So again, we have height of people. That's going to be continuous. Money earned last week. Well, this one's a little bit different because this one is discrete. So while it does have decimal values, in other words, $6.33, it is discrete because we don't get any farther than to the penny, 33, And in fact, the next value you could get from there is $6.34. So in other words, there's no values that we could have in terms of monetary that's in between $6.33 and $6.34. So in that makes sense, it makes it discrete. Number of siblings is also discrete as well. Speed of a train, so here we're talking about sort of time over distance or distance over time. So again, both of those are continuous, so that makes that continuous. The sum of a pair of rolled dice, so this one is discrete because you only get the values of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. So nothing in between. So this is definitely discrete. Dominant hand reaction time. So again, anything to do with time in this case is going to be continuous. The number of languages spoken. You may think you could speak half a language, like I speak half Cantonese. True, I guess, if you want to go to that granularity. But we're not going to, for spoken languages, you either speak or you don't. Really, that's how we define it. So in this case, it's going to be sort of discrete. And color of a car, well, colors are definitely discrete. It's definitely not continuous there. Okay, so there's an example of that. Let's look through a numerical example. So the value of a new car purchased at $78,000 depreciates. In other words, it loses the value at a rate of 15% the first year and then 4% after that. So number A says determine the value of the car at the end of the first, second, and third year after purchasing and write these values as a sequence. So we could think here that time, basically time is a year, that could be sort of our term number. So n would be 1, meaning that what's the value of the car after 1 year. N would be 2, would be what's the value of the car after the second year. And n being 3 would be the value of the car after the third year. So here we can think of it as a sequence. But in this case, n, the term number, could represent our year as well. So let's look at how we determine what the value of the car is after the first year. Well, we just take the set calculation, 78,000 times, well, if it depreciates 15%, really what's left over is 85%. So we can do this calculation of 78,000 times 0.85, and that is 66,300. Okay, just sort of to prove this formula here of multiplying by 0.85 is that here we could, let's say that we take this rate of depreciating by 15%. So how much does the car actually depreciate by? Well, it's going to be 78,000 times 0.15. But this is the amount that it depreciates by. So that's the depreciation. In other words, that's how much is lost. But we need to subtract that from what it originally started at. So it's really going to be 78,000 minus that, and this gives me the new value. Well, if I factor out 78,000, I get 1 minus 0.15. And this turns out to be the same thing as 78,000 times 0.85. So this is why we can sort of take that shortcut there to figure out what the value of the car is after certain depreciation. So that's the 1 year. So here in this words, we could say maybe T of 1, in this case, is 66,300. Well, what's T of 2? In other words, what's the value of the car after the second year? Well, it's going to be this amount. In other words, what it was worth after the first year. But it says after the first year, the car depreciates 4% for every year after that. So in this case, we're going to multiply by 0.96. So 66,300 times 0.96 is 63,648. So that would be the second term. And what was T3? What's the value of the car after the third year? Well, it's going to be the value of the car after the second year. So 63,648, and we multiply again by 0.96. So in this case, that's going to be 61,000 $102.08. So here we're going to write the values as a sequence. So here's the sequence, going to be 66,300. It's kind of weird because I have a comma and in my number, and I'm going to separate my numbers by comma. Next one is going to be 63,648, and then $61,102.08. Okay, so and then we can say that sequence kind of continues. How can we determine the explicit formula for the value at the end of a given year? Well, here we can say that what's the common pattern that's happening is we keep multiplying by 0.96. And notice here we sort of generate a formula for this. We can say T of n. Well, it's going to start off as 66,300. And then we're going to have to multiply this by 0.96. But what's the relationship between n and how many times we're multiplied by 0.96? So in this case, we could think of it as after the second year, we're multiplied by 0.96 twice. After the third year, we've had to multiply 66,300 by 0.96 twice, because really 63,648 was really 66,300 times 0.96 times 0.96. So here we could say that in general, we could say that we're going to take 0.96 to the power of n minus 1. So that could be a general formula. So that's B. C, and this is why we want sort of the explicit formula, is that we could calculate the value of the car after 20 years. So here we say, well, after 20 years, in other words, what's the 20th number of my sequence? That's T of 20. That's going to be 66,300 times 0.96 to the power of 20 minus 1, which is 19. And take that in my calculator. And the answer is $30,525 and roughly 79 cents. Okay. Next question. Well, I'll ask you part of C. Is this realistic? If a car is still initially worth 60-something thousand and is still worth 30,000 after 20 years, that's a pretty good deal. So a couple of things is maybe the 4% depreciation is kind of low. I also think it is. But in reality, cars don't depreciate at the same rate every year. So this one's a little bit unrealistic. Maybe it might for the first 5 years or 6 years, but not definitely over the span of 20 years. If you want to think about an extreme example, we could do T of 100. In other words, what's the value of this car after 100 years? Well, if the car could survive 100 years, that's pretty impressive. Let's answer D. Is this continuous or discrete function? Well, this one's a little bit tricky because we could say that, well, do we only take the value of a car after every year? Technically, we could see what the value of the car is after half a year, a quarter of a year, after 5.5 years, because people don't sell cars exactly on the anniversary date that it was bought. But in essence, you could get down to a granular level of a day. We're not going to go down to maybe a second. So in this case, I would call it that this is discrete. And usually when you determine the value of a car, you are going by years or half a year. You sort of do something that's in between. Well, it's worth after 5 years, it's worth about this. After 6 years, it's worth about this. Was after 5.5 years, and this is where we're sort of ballparking and something that's obviously in the middle between the two. But here we're not going to. You won't get a value of a car for every single second that's gone by. So in this case, I would consider this function to be discrete. So in our textbook, I basically covered everything from in 6.1, the notion of sequences as discrete functions. As part of this lesson, I'm going to talk about recursion as well. So that's 5.2 in the textbook, but it's a bit of a straightforward concept. It's tricky in some sense. I know in computer science there's the idea of recursive formulas and recursion in our programming, which gets pretty tricky to understand. But actually, in the mathematical context, it's actually not too bad. And actually, in looking at your sequences, it might be easier to look at sequences in terms of how is it related to the previous number. And that's really what recursion means. There are also some sequences that we could define through recursion, but there might not be an explicit formula for that. Okay, so here we're going to talk about recursive formula. So by definition, it's where each term is generated from the preceding term or terms. So for every recursive formula, you're going to have two parts. So when I ask for a recursive formula, you must state two parts. You must state the two parts because one without the other doesn't make sense. And it's incomplete in that sense. So the first thing is that you need the initial set of terms or the starting point. What is your starting conditions? The second is you can have an expression of a term that's based on the preceding term or preceding term. So it could be just one term, it could be two terms. It doesn't necessarily have to be the term right before it. It could be the second term before it, but it's based on something that has happened before, and that's sort of how you define it. Okay. Sometimes the best way to sort of see and understand recursion is actually looking at an example. So here we're saying that the first term is 3. And this is how we sort of define a recursive formula. So we need to be careful when we see that t of n minus 1. Notice that the n minus 1 is still subscripted. And that's all it's saying is that while t of n minus 1, well, if t of n is a certain term number, so let's say t of 5, t of n minus 1 is really the term before that. So in this case, if with t of 5, n was 5, so 5 minus 1 is 4. So that means that whatever the fourth term is plus 2. And this is why it's really important that we need that starting condition. So in this case, I'll do it explicitly. We're going to say t of 1 is 3. So I'm going to just write this over here as 3. Well, what's the second term? So I'm going to write this on the side is, well, we're saying the second term is going to be t of n minus 1, so really t of 2 minus 1, which is the first term, plus 2. So in other words, the second term is really the first term plus 2. In this case, what's the first term? Was 3, so we're going to add 2 to that, which is 5. And we see, and this is a nice thing about the recursive pattern, is that we're just saying that the next term is the previous term added 2. So once we sort of see the pattern going, we're going to say the next term is going to be 7 because what's the previous term is 5. And what's t of 4? Well, t of 4, or the fourth term, is really the third term, add 2 to it, and we're going to see that's 9, and we'll see that's going on. So sometimes it's actually easier to write a sequence based on a recursive formula than a general term. Let's look at the next example, and actually this one I sort of wrote out as a function notation. Okay, so really this is the same thing as saying that the first term is 6, and the nth term is minus 2 of the previous term plus 1. And notice that here, when we talk about the expression based on previous terms, we always have to state that, well, this is for n when n is greater than 1. Well, this is important because when n is 1, in other words, we want to find the first term, we cannot use this formula. We cannot use the recursive formula because there is no 0th term. So that's why it's important that we express what the first term is, because when n is 1, we actually use that definition of t of 1. So let's write out the sequence of this one. So the first term is 6. And really what our formula equation is actually saying, or recursive equation, is to take negative 2 multiplied by the previous term, and we want to add 1. So in this case, the second term is going to be negative 2 times 6, which is negative 12, plus 1, which is a negative 11. The third term is going to be the second term multiplied by negative 2. So negative 11 times negative 2 is 22, plus 1 is going to be 23. And then the fourth term is going to be the third term multiplied by negative 2, which in this case is negative 46. And I'm going to add 1, which is 45. Okay? So that's how we come up with a sequence given the recursive formula. Now we sort of have to work backwards and say what the recursive formula get based on the sequence. So this one, in some instances, isn't too bad. Again, we're looking at a pattern. What's the relationship of, let's say, one number compared to the number before it? That's usually the easier way to look at it. Hopefully, it is based on the previous number. So the nice thing about recursive formula is the first part is always easy. T of 1, well, what's the first term? 2. Well, in general, in this case, we see the numbers are going up by a factor of 3. In other words, we take the previous number, multiply by 3. So here we get 2, 6, 18, 54. So in this case, the recursive formula would be 3 times my previous term, which is t of n minus 1. And again, to state that this only happens when n is greater than 1. The next sequence, what might be the relationship or the pattern here? Here we see the numbers are going down by 2 every single time. So really we're taking the previous number and subtracting 2 from it to get our current number. So again, we need to express the initial condition. In this case, t of 1 is negative 3. And then t of n is really the previous term. So t of n minus 1. And we're going to subtract 2 to it. And this happens for the term numbers that are not the first one, or term numbers are greater than 1. So that's the idea of recursion. It's actually really neat. It simplifies things a lot better, easier than going off and looking at the general formula where, if you want to keep doing the second term, third term, you have to keep plugging in n equals 2, n equals 3 to your equation, and then doing the calculations and getting those term numbers. So recursion is a bit easier in some sense to get your list of sequences. Sorry, it's the terms in your sequences. So here's an example that we could sort of use recursion. So a runner injures her knee in a race. Her doctor prescribes physiotherapy along with 500 milligrams of an anti-inflammatory medicine every 4 hours for 3 days. The half-life of the medicine is approximately 4 hours. So that means after 4 hours, about half of the medicine is still in the body, which is, I don't know, to me kind of scary. Anyways, so here we'll make a table of values to show how much medicine is remaining in the body after each 4-hour period of time. And then we want to write it as a sequence, and then perhaps come up with a recursive formula, and then perhaps describe what happens to the medicine in the runner's body over time. So let's first of all come up with a table of values. So let me draw a table. And here we could say, let's look at t. So t is really the number of 4-hour intervals that we have. And this is going to be the amount of medicine. So the equation we come up with here is, well, when she first takes the dose, so 4 hours have passed by, how much medicine is in her body? Well, it's going to be 500 milligrams. The next time she takes the medicine, so 4 hours later, so this would be really the next number of her sequence, is how much medicine is in her body. Well, it's going to be whatever was in her body before the 4 hours, so after the 4 hours, but only half of that, so that's what the half-life means. And then she just took another pill, which is another 500. So in this case, it's going to be 250 plus 500, which is 750. So we just continue with this pattern. Her second time that she takes the medicine, or really the third time she takes the medicine, but it's after the second 4-hour interval, is going to be 750. In other words, the previous time times a half plus 500. So in this case, that's 875. Let's look at the third one. So that's going to be 175, and we can almost see what the recursive equation is going to be. So that's going to be 937.5. So the fourth time or fifth time she's taking this pill, that's going to be now 937.5 times a half plus 500. It's going to be 968. So you can see that the amount of medicine that's remaining in her body is actually growing, going up and up and up. So after the fifth time, it's going to be 968.75 times a half plus 500, 984, 3.375. The sixth time or the seventh time after is going to be 984.375 times a half plus 500. It's a good thing I can make use of the answer part of my calculator, because really I'm just taking the answer, multiply 0.5, and then adding 500 again. In this case, it's going to be 992.1875. The seventh time, and I'm not going to rattle anymore, but I'm just going to do the calculations. So it's going to be 996.09375. Let's do a couple more. 8 is 998.046875. Maybe 999. So we're getting really close to 1,000. 0.234.375. And let's just do one last one. Let's see if we can hit 1,000. Nope, we get 999.5117188. And we could continue this pattern, and we're going to get really close to 1,000, but we're never going to get hit 1,000. And it kind of makes sense. If we keep losing a half, you're never going to get back to 500, and we keep adding 500. So it's going to get close to 1,000, but not there. So there's A. So we'll write this as a sequence. So it'll be 500. So this is B, 750, 875, 937.5, and so on. So we can write the rest. More interestingly, how can we write this formula as a recursion? So we can kind of see what's going on there as we're doing the calculations. Well, the first one is 500. So that's always the easiest part of a recursive formula. Well, how do we get the next one? Really, how do we get the next one is we did half of the previous one, and then we added 500. So coming up with the recursive formula isn't so bad as long as we kind of see what the pattern is. And D, what we discover, it gets closer and closer to 1,000 milligrams in the body, but doesn't quite get there. Okay, so that's the idea of recursion. I do want to talk about one other famous recursive set of numbers. It's called the Fibonacci sequence. And the Fibonacci sequence is like this. It's actually a lot of practical. It turns out that the Fibonacci came out of this sequence. I'm not sure how he came about it, but the numbers that come up appear in various parts of the real world, which is really interesting. So anyways, the Fibonacci sequence is this. It's going to be 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on. If you think I memorized that, then that's you give me more credit than I deserve. My memory sucks. What I have memorized is how the Fibonacci sequence works. It is recursive, and that's what I was doing as I was writing it out. I was actually calculating the recursive formula behind it. And seeing the recursion behind this is a little bit tricky if you haven't seen it before. So in terms of recursive formula, this one is a little bit unique. So you might think, well, I got the first term as 1, the second term as 1. Well, the only relationship between that is the same. So that would make the third term 1. Well, in this case, it's not 1, it's 2. Well, what's the relationship between 1 and 2? It goes up by 1. That might be a hint, because when I go from 2 to 3, it does go up by 1. But that all breaks apart when I go from 3 to 5. because that's not going by 1, that's going up by 2. And you kind of see, well, in between there, it's going up by 3. Between 8 and 15, it's going up by 5. Going by 13, 21, is there a pattern there? That's going to be difference of 8. And then we kind of see, oh, wait a minute, going up by 3. That's one of the terms in my sequence. Going up by 5, that's another term in my sequence. So a Fibonacci sequence actually turns out to be like this. It actually has 2 initial terms or initial conditions. So really we're saying that the first term is 1. The second term is 1. Okay, but the rest of the terms is based off of these or previous terms, and it looks like this. T of n is basically how do we get our second term or third term is you take the 2 terms before it and add it together. That's how we get 2. But for how do we get the term after, how do we get this term now? Well, we take the 2 terms before that, so in case 1 and 2, add them together, and that's how we get 3. How do we get this term over here? So this is the 5th term. Well, we need to take the 3rd and 4th term and add together, we get 5. And this is how that pattern continues. How do we get the 6th term over here? Well, we need to take the 4th and 5th term and add them together until we get 8. So what we do to get the term is we take the second term before it, so t of n minus 2, and we're going to add the t term just right before, in this case t of n minus 1, and this is how the Fibonacci sequence is defined. So that's a kind of a really neat sequence. I'm not sure if it's in the textbook or not, but there's just a nice thing to sort of to be exposed to and introduced to. I know for those who might be taking computer science in grade 10, going to grade 12, I do a little example of Fibonacci sequence in our programming next year. So please remember that. Anyways, here's the homework for both sections. So this is basically on sequences, and 370 is based on recursion.